So we actually have another talk on Viper right now. This is more of the science-focused talk, and is going to be given by the scientist, the lead scientist for Viper, Dr. Tony Colaprete. And Tony, in addition to his current duties, was also heavily involved in LCROSS as well as its project scientist. So Tony, take it away.
Yes, I'll talk about more of the science measurements and observations and the traverse plan that Viper is considering as we go forward. I'll not read each of these bullets here, but as this is recorded, you can come back and review at your leisure. Viper is about characterizing volatiles, including water, of course, really trying to understand their distribution. At very low concentrations, we want to measure down to at least 0.5%, but the instruments are capable of making observations much less than that, 0.1% or even less. The spectral range and mass range of the near-infrared spectrometer and mass spectrometer cover a wide range of key volatile species, everything from molecular hydrogen out to ammonia, methane, and of course, water. It is a mapping mission, and I think this is quite unique about Viper in that it is really at its core trying to understand the distribution and abundances of these volatiles in a statistically meaningful sense across both lateral and vertical scales. That's really important if you want to understand the resource potential of these volatiles. It's a page out of the USGS playbook, if you will, and we are adopting those techniques, geostatistical mapping, core sampling series techniques to understand the distribution. It's also very much a science mission in that we have a litany of direct science objectives and hypotheses that we're going to test with the mission by making these various measurements here that I've listed. Now, I mentioned it's all about volatiles and mapping. Of course, understanding the context of which you make all these observations is critical. And Bethany commented on this with regards to temperature. Temperature is key, we think, for volatiles at the poles. So we measure temperatures, but we also measure other things, including subsurface temperature, mineralogy, geomechanics, composition, etc. Because all these things we want to pull together into a better understanding, better predictive capability for understanding where volatiles, especially water, could be located. Here's the 4 instruments that, science instruments that we have on the rover. Really quickly, the neutron spectrometer, Dan mentioned, is our hydrogen nose out in front of the rover. We have the M-SOLO mass spectrometer, near-infrared volatile spectrometer system, and then the Trident drill. And this table captures some of the key observations each of these instruments make. NSS measures water equivalent hydrogen, measures hydrogen while roving down to a meter. This is key to get the adequate density of observations to make a good statistical prediction with a known confidence level. We need an instrument like this to constantly be observing subsurface hydrogen. Nervous and M-SOLO are on continuously while driving too, and they tell us everything about the surface in terms of composition, temperature, high resolution imaging, and key isotopes while driving. Then finally, Trident samples down to 100 centimeters in 10 centimeter increments, brings up samples for both M-SOLO and Nervous to sample. Whoops, I've got it on a timer, which is not what I wanted. Okay. And also what's important about Trident is it measures subsurface temperature in 2 locations. It's got 2 temperature sensors, one located at the bit, one above it by 20 centimeters. That's going to provide a wealth of confirmation data of the predictive models of thermal models that we have. Right now, we don't really have a lot of subsurface temperature measures, none at the poles. So that's going to be a really unique observation. I mentioned the instruments are on while driving. So we have really 2 modes of operation. There's prospecting and there's drilling, science operations, that is. This slide represents what's occurring during prospecting. We have the neutron spectrometer, the nervous system, and M-SOLO on continuously while roving or parked. And this little graphic just illustrates, what we're, as we're roving along, we're making these measurements all simultaneously. So again, it's exactly what Bethany was talking about, making simultaneous observations of temperature, hydration state, subsurface hydrogen while roving. Being able to pull all that data together continuously is critical. Is so much more powerful than if you just made individual observations one separate in time. While drilling, we have M-Solo and the near-infrared spectrometer on, observing the cuttings pile, as Dan described, a 10 centimeter bite at a time. And what we do is we bring up the cuttings, we brush them into a pile, we watch them for a number of minutes, 5 to 10 minutes, until everything's sublimed out of there. And then we go back down and we take another bite. At the bottom of every drill, we stop and pause to take a subsurface temperature measurement. What's really interesting about this observation, in my mind, amongst other things, is that we get to see both the water in its solid state. Nervous as a reflectance spectrometer gets to observe whatever volatiles are there coming in as ices or adsorbed water. And then M-Solo gets to see the volatiles as they come off and sublime. And that's really makes a great combination for, again, observing how are really constraining the state of volatiles in the subsurface. So where are we going? There's a number of constraints on this mission, being solar, direct earth communication, slopes, trafficability, roughness. It's this giant matrix of ands. So we'd be pretty much left with actually a small number of areas at the poles of the moon where all these constraints can be met. The good news is there are several areas, and they're shown here highlighted in yellow. These yellow areas are areas where we have locations with less than 70 hours of shadow over our mission period. So we call these safe havens. When the Earth sets and we can no longer communicate, we have to park the rover. We park in one of these safe havens where it has continuous sun, except for 70 or so hours, and it can easily survive on battery power. We awake the next day and continue the mission. And you can see in the background overlay is the Lunar Prospector hydrogen map or neutron flux map. And here's Cabeus, where L-Cross impacted right there. And the areas we're looking at in particular are the Haworth area, the Nobile area, and an area down here in Shoemaker. The insets here show what we call ice stability regions. So we divide up the areas where we think water could be stable as a function of depth and temperature into four zones: one surface, one shallow, one deep, and one dry. Dry meaning in the top down to a meter deep. We expect temperatures to be too warm to ever have water ice. Stable, red being at the surface, like a permanently shattered region. We expect water ice, the temperatures to be cold enough for water ice to be stable there. At each of these locations, we're building a range of traverses. We've been doing this for years now, and we get higher and higher fidelity each and every year, every cycle we do on this design. This shows just a general structure of the traverse plan. In each lunar day, here's each one of these yellow bars is a lunar day, a lunation. This leg is when we're active. Leg one is when we're active during the lunar day. And then this hibernation period is when the Earth has set and we have to park because we're a direct-to-Earth communication rover. In each leg, we have what we call rails driving and then science stations. Rails driving is how it sounds. You're on a rail, you're going as safely and as efficiently as you can to your next science station. All the instruments are on all the time, regardless. But here science is not in the decision loop. It's really just rover operators getting the rover to the science station. At the science station, which is represented here, we have a traverse plan within it and various drill sites. Here, science is in the decision loop and actually guiding the rover and including location of drill sites. You're looking at real-time data. So it's a very integrated mission, integrated between science and operations. And it's a real-time mission, which is going to be is quite unique and going to be quite exciting. This is an example of a traverse. This is for the Nobile study site region. It's just an example, but a recent one with the most current rover capabilities. Real quick, this map here on the right shows an area near Nobile. These ice stability depths I mentioned before are shown here with this key in these colors. These three PSRs are key PSRs we're targeting in this area. They're fairly large and quite old based on the estimates the science team has given. This is about 500 or so meters across this permanently shadowed region. This little bullseye over here is where we have come down and landed. And the green lines show the rails driving to each of the science stations. These little circles indicate either a science station or some kind of activity like a recharge or a hibernation. These little gold circles or gold squares here are the safe haven locations. You can see we come to these safe havens, for example, here periodically to survive Earth down. This is a really fun traverse, in my opinion, because we get to visit all three of these PSR locations and make measurements all along the way. Some statistics on this particular mission. This one is fairly long. It's at least 4 lunations long. And we mapped out 106 days with 28 more total operational duration. The total traverse distance on this is 27.4 kilometers. So as Dan was saying, this is a pretty sporty little rover. We're going to do not quite 30 kilometers in 106 days, which is pretty great. And actually just 45 days of operation. The other days is when we're in hibernation. We have here in this plan 12 science stations, and this is the breakdown between them: 2 PSR, shallow, deep, and dry. And that's quite that's the minimum number. We certainly can probably add more to these. That covers a total map in the science stations only. We're mapping over or close to 4,700 meters squared of real estate, and have 32 drill activities. So this is really going to provide a lot of data at very high resolution. Okay, let's go to the next slide. Real quick then, those plans that you saw were done on basically a data set that's a 20-meter resolution, including LOLA, DEMs, digital elevation maps, thermal maps, et cetera. We've been working very hard over the last year or two on high resolution data products, and this is an example of one. We have a shape from shading DEM, which is at 1 meter scale, made from LRO LROC NAC images. And then we use that DEM, 1 meter DEM, to calculate slopes, calm, sun, et cetera, but also temperatures. And this is a product that Matt Siegler, who's a co-an on the Viper Science team, has provided. And it shows really the unprecedented detail of thermal prediction that we're capable of having with thanks to NAC imagery and the awesome modeling that Matt and Dave Page can do. This is, if I jump up real quick, this is a zoom in of this PSR area right here. This is at 20 meters. So not bad resolution. This is what it looks like at 1 meter resolution. You can just see the structure is incredible at this scale. We knew this would happen. We plan at these scales now. And then you can see here we've drawn in this particular example. This was for a science operations sim that was conducted. We have a dry science station here, and then a deep and a shallow. And we go into each of these science stations and we plan them at this level. This is now zoomed in. Each of the pixels on this map is 1 meter. Each, you can see the little dots here. Those are what are called drive segments. In between each of these dots, the rover drives in a waypoint fashion, about 4.5 to 5 meters at a time. At each waypoint,
1 minute.
Thank you. This is like my last slide. Each of these points, the rover stops so we can take navigation images. And at the same time, we take a series of images from the Nervous imager, multicolor images there, et cetera. So all along these segments, we have every 5 meters a wealth of data coming in. Also at each of these points, we do a panorama to help with navigation. So one of the things we've done over the last year is really turn the rover camera suite into a science instrument. It was never meant to be, but it's critical data. We're working closely with the rover imaging team. All that data, rover imaging data, is going to go to the PDS, et cetera. So we're going to have a wealth of image data too, at really unprecedented coverage across these scales. as well. And I will end there. I don't need a preaching to the choir here. I don't need to really say how incredible the last decade and a half has been in terms of discoveries at the moon and rewriting textbooks, etc. Viper really will conduct a next level of exploration at the poles of the moon, getting down to the surface, having mobility of many kilometers, and looking both at the surface and subsurface in ways we haven't yet. Hopefully it will really feed forward to both exploration and science next steps leading into Artemis and beyond. And with that, I thank you. The last thing I will say actually is the last bullet there. We are really excited and looking forward to bringing on new science team co-investigators with the call out right now. So really looking forward to bolstering and improving the team. And that's it. Thank you.
Awesome. Thanks, Tony. And I can't wait. This is going to be such an enabling mission. And boy, what an exciting thing.